Here we go, page 6. So again, I know this is monotonicity, it's hard to say, concavity, and then connecting the original function and the two derivatives in their graphs. Something we've done before, but we'll do a little bit more of. You know, the only time you might see concavity is like, remember, like convex and concave, like that was a concave polygon. So the idea is just the inside motion curvature of that, I guess. Anyways, we'll talk about that probably more tomorrow. Increasing and decreasing functions is what I'm going to focus on first. Now, I think you know what increasing is, correct? We read left to right, so increasing would be like that, and decreasing would be that. The first thing I say here is the mathematical definition. F is increasing on a given interval, I. If x1 is less than x2, here's what this means. Here's x1 and x2. Would you agree x1 is less than x2? So if that's true, and f of x1 is less than f of x2, that just means the y values. So the y value at x1 may be here, the y value of x2 is bigger. If that's true, then the function is said to be increasing in the interval. It doesn't have to connect like that. It could connect like this, but it's increasing on that interval. By the way, suppose that it went like this. Well, I'd have to break it up more, and I could say it was increasing from here to here, decreasing from there to there. I have to break it up more. If the same setup is true, but the x1 value is up here, it's bigger than the x2 value, then set it to be decreasing on that interval. That's just the mathematical way of increase and decrease. Which leads us to the monotonicity theorem. This is an important one. Okay, how do we know, based with calculus, that a function is increasing? And how do we know that it is decreasing? What? Well, we look at something that sounds pretty common here, the derivative.
We look at the derivative for everything.
Well, we're still in the more, this is the even more derivatives unit.
How many more units of this are we going to go through? I feel like that's the whole year.
No. We're limits, derivatives is about half, and then integrals is about half. So we're almost done with derivatives. Now, I want to go down to this down here. This is it's on the right side of your page. I moved it, but hey guys, this function right here, it's kind of got a maximum right there. It goes up and down. Would you agree that right here at that point, the slope, that little line drawn, the slope is going up for that tangent line?
Yes.
Oh.
And if I chose this point right here, the slope is going up. Its tangent line is positive.
Yes.
And right here, the tangent line slope would be positive. And right here, the tangent line slope would, and right there.
Till 0.
And, well, until that's
Until the
actually.
velocity is 0. Or the tangent line is 0.
So would you agree that right here, the tangent line slope, in other words, the derivative, is positive?
Cool.
The slopes are positive there. And then the slopes on this side, if I took a single point or any of these points and looked at the tangent line, wouldn't the slopes be negative?
See.
On the right side? This is the calculus mathematical way we can say increasing and decreasing. It's increasing if f prime is positive, and it's decreasing if f prime is negative. So that's what this theorem will say up here. As long as we have a continuous function, and it's on a closed interval, and it's differentiable, should sound familiar, then we say it's increasing if f prime is greater than 0. That's saying positive. I said positive up there. If f prime is positive, at each point of that interval, then f is increasing on the closed interval. Same thing, but if it's negative, then it will be decreasing. All this is saying is the slopes are positive, that means it's increasing. If the slopes are negative, it's decreasing. Okay. I'm just going to try an example with that, where here's a function, find where f, the original function, is increasing and decreasing. Thoughts before I do? Okay. We're finding where the slopes are positive, that's increasing, and finding, yeah. So right now, increasing is where f prime is greater than 0, decreasing f prime less than 0. Positive and negative. What we're going to do, derivative of course, because it's going to look just like the extreme value section, where I actually find the critical points. Alright? So it's going to look very, very similar to the first half of this. So I do the derivative. There's no endpoints, by the way. I do the derivative. Power rule 6x squared minus 6x minus 12. Okay, now what I'm really doing here is I need to solve first. So you can write this as you want as a guide. I'm not actually going to do exactly this. But I need to find when it's greater than 0, increasing, and less than 0 when it's decreasing. Do you see what I've formed is a quadratic inequality? I'm looking at this. Where that is greater than 0 or less than 0. It's quadratic inequality. This was probably the first thing you did in Algebra 2. Or somewhere in the beginning of the year, Algebra 2 stuff.
Yeah, well, that was a while ago.
It was a while ago. We did one earlier this year. You probably didn't do, if any, in pre-calc. So I know it's been a while. Here's what you do with these quadratic ones. You solve it as if it was equal to 0.
Oh, wait, I know this.
And I'll get the critical points. Do you know what we do next then?
I think so. You solve it. For x.
So yeah, well, here, I'll keep solving it and see. So we solve it as normal, equal to 0. And we're going to get our critical points. But then we do something else. So I'm going to factor out a 6. GCF, x squared minus x minus 2, 0. I can then factor this trinomial, x minus 2, x plus 1. I get 2, I get negative 1. Notice I get nothing from 6. Because it would be 6 equals 0, not 6x equals 0. Okay, so those are the critical points. That's extreme values. That's horizontal tangents occur there. Do you know the next?
Then you put them back in.
You're close. You're close.
You put like one back in. Right?
I hope maybe your teacher did it slightly differently, but usually you see this. You make a number line, and you have to choose values and plug those in.
Is that we did that at the beginning of this year?
We did it. We did it once or twice with Unit 3. It was when we were doing first and second derivative,
But you
some
didn't find
velocity.
It that, like, the velocity is.
We did it, yeah.
That the velocity was like.
Where was the velocity increasing or something? Yeah. Okay, so hopefully this will look familiar after I do it. But you make a number line. So I know the slope at negative 1 is 0. And I know the slope at 2 is 0 for this function. But what's happening in between? So the answers to these questions are intervals. It's not increasing at one point, it's increasing on an interval. So you do test values. I choose a value to the right of 2. I choose 3. You can choose 3.14. I chose pi. You could choose 17. Any number to the right of 2. I'll choose a number between negative 1 and 2. I choose 0. And a number to the left of negative 1. I choose negative 2. I try to choose easy values. Now, I'm testing to see slopes.
Do you put in the derivative?
That's what I was going to say. That's correct. So this is an important difference. So at this point in the unit, guys, and moving forward, some of the work isn't always that hard, like the derivative and factoring. But then you're going to be like, where do I plug it in? What do I do with that number? So that's the tricky part. I'd like for you to think of it conceptually. If you're trying to see increasing, you're looking at slopes. Where are the slopes positive? That's increasing. So that will guide you. It is going into the derivative. Because think about it. If I plug negative 2 and 0 into the original function, I'm getting a y value. I'm just getting a point. Okay, and also, by the way, intervals, you'll never, when you do an interval like this, you're never going to plug it into the original, the test values. So that negative 2, 0, and 3, you would never plug that into the original. Okay, so I'm plugging these into the derivative. which I boxed here. Let's do it. So I'm going to start with 0. Usually that's the easiest one. I plug in 0 here. It'll be 0 squared times 6, that's 0. Minus 0 times 6 is 0. Minus 12. That'll be negative 12. I don't actually need the exact number. I just need to know if it's negative or positive. So all I'm going to do is put a negative sign there. I'm going to do 3 next. Again, you could calculator, scientific could help. I'll do it by hand. So I'm doing it here. 3 squared is 9. Times 6 is 54. Minus 6 times 3 is 18. And minus 12. That'll be a positive number. That's 54 minus 30, which is 24. Finally, let's plug in 2. And I plug in negative 2, I'm sorry, negative 2. 6 times it'll be 4. Negative 2 squared, positive 4. So that's 24. Negative 2 times negative 6 is positive 12. And then negative 12. And so I get 24, which is positive. By the way, they are not always alternating. That does happen, yeah, probably more often than it doesn't, that they alternate. But really, there's not a set pattern. So I don't think that they're always going to alternate. Okay, here's something I'm going to start doing. I haven't focused on this as much in the past, but I want to moving forward. We are done with these test values. So I want you to just cross them off. You can just cross them off individually or just get rid of them altogether. The reason is because students will then say, oh, it's increasing. Here's what I've had in the past, too much. Students will say it's increasing between negative 2 and 0. And I'm like, well, no, those are just the random values you chose. Now, it doesn't have to, it's increasing on the entire interval up to negative 1. So just cross off your test values. That's what I'm going to tell you to do. That's what I'm going to do up here. We're now ready to write our final answer. F, the function is increasing on the interval where it's positive. Everything to the left of negative 1. So that's negative, this interval notation. It's negative infinity up to negative 1. Union, because it's positive over here as well. 2 is the starting point up to infinity. These will never be closed brackets. Infinity is not a closed bracket. And these will never be as well because the slope here at negative 1 and 2 is 0. It's horizontal. Thank you. And finally, decreasing. Where it was negative, that's between negative 1 and 2. So negative 1, 2. Okay. Sounds good. Anything I can clarify on that one? Notice we plugged our test values into the first derivative, not the original. Original would always give you the y values. So that's the difference. Extreme values we plug into the original. Move on. Okay. Let's see. I say here a couple of things. So we're moving on. The next thing is finding local extreme values, local extrema. Sometimes we've known if it's global or local, but in general, there's a rule to know if it's global or local and how we test for that. We're going to apply the monotonicity theorem into what we call a first derivative test. This is very, very important. This is a test for local extreme values. Hopefully this is one that just makes sense to you. Remember this one, guys, this diagram is increasing, then decreasing. Would you agree if any function increases on the left side and then decreases on the right side, it's a maximum? Right? That's a max right there. And if it decreases, let me use this grid. If it decreases on one side, but on the other side it increases, would that be a minimum? It's a valley, that's graded. All we can say is it's a local max. It could be, for example, if I have the function negative x squared, increasing and then decreasing. Increasing, decreasing. That one would be a global max. But all that this test will say for sure is if it increases on one side, the left side, then decreases on the right side, that it's a local max. Could be more, could be global, but we know it's at least a local. That's what this test says, the first derivative test. Has to be a continuous function again. If f prime, the slope, changes from positive to negative, it's a local max. That was this one. If f prime changes from negative to positive, it's a local min. That was this one. And if f prime does not change signs, then a local extreme value does not exist there. So here's an example of that. It was increasing this function up to there, up to C1. Then it kept increasing. So temporarily, just at that single point, it was level. So that would have been a critical point, but it didn't change sign. So we cannot conclude it's a max or a min. All right, we're going to try an example of that on the next page. And I say at the bottom there, just a summary, local extreme values and increasing, decreasing, first derivative. Do you see it? For some reason it's not up here. Do you see it? So extreme values, if you want the actual max or min, original function. Increasing, decreasing, and local max min, to find those, you plug it into the first derivative. Okay. Let's flip it over then to the next page, try a few examples on that. Is there anything else I can answer though on that before we try these? All right, so top of the next page, from the previous example, this is the one we just did, where we found critical points -1 and 2. Thank you. -1 and 2. And we found that it was, no, it was negative in the middle, right? Is this? Guys, I'm just basing off the last one. Determine the relative, / local, same thing. Extreme values. And here's what we can conclude. Since it was, this was the slopes. So here's the slopes. So the original function, it was increasing up to -1. Then it was decreasing, that should be a corner. Then it was decreasing to 2. And then it was increasing. So I can conclude from the first derivative test, there's a local max at x equals -1. And there's a local min at x equals 2. So max because it was increasing and then decreasing, min at 2 because it decreased and then increased. It could be more to global, however, actually it's not on this one, is it? Because x cubed, there would be no global max or min, just goes on forever in both directions. Now, if you wanted the actual maximum value, then you plug -1 and 2, well, max and min values, -1 and 2 into the original function. Okay, let's try 2 more to finish up with this concept. Increasing, decreasing, local, first derivative test, local max and min. Good. So I'm going to move on, try the next one. This one, kind of a summary of things. Critical points, local extreme and global extreme values. Okay, so we start with A here. Each of these starts off the same. You do the derivative. I get 3x squared. Critical points and the first derivative test. You have to find the critical points, set it equal to 0. I will divide both sides by 3. 0 divided by 3 is 0. And then I'll do a square root. So we get plus or minus 0, which is 0. It's not 2, just 0. But that's critical point. There, maybe I should label it. It's the x coordinate of my critical point. Now what I'm going to do is test local extrema. First derivative. So I'm doing first derivative test. First derivative test. And then I'll check based on that. Well, here, you know what? Since it's x cubed, can't I already say there's no global extreme values? It goes on forever in both directions. So there's not going to be any of this one. Derivative test. Okay, so what am I doing? Well, I'm doing a number line. There's 0. I only have one value this time. Last time it was 2. So I'm going to try a value on the right side of 0. I'll try 1. A value on the left side of 0. I'll try -1. And I plug, again, test values, I'm going to write here, you plug into the first derivative, 3x squared. So when I plug in 1, 1 squared is 1, times 3 is 3, that's positive. When I plug in -1, -1 squared is 1, positive 1, times 3 is 3, also positive. So what we can conclude is it's increasing with f, the original function, increasing up to 0, then increasing after 0. Was there any change? Was there any change? No. If it does not change signs, then the local extreme value does not exist. So, local. So I'll just put local there, and there's. Again, the reason is because it did not change signs. If it went plus to minus or minus to plus, we'd be good. And again, there's no global either, because it's x cubed. There was a critical point, but no, there's no action then. As this function, it just looks like this. It levels, but then it keeps going. So just at one point, the slope is 0, but it doesn't actually become a maximum min because it doesn't go back down. By the way, if it said increasing, decreasing, we'd say it's decreasing nowhere. And it's increasing, we would say from -infinity to 0, union 0 to infinity. That's the way to say everything but 0. Because at 0, the slope is 0. Oh. Back here. Okay. Well, should we go on to part B? Any thoughts on part A? Very well. Part B it is. A different function. Well, critical points. Gotta do the derivative. G prime of x. I have two values, what really a binomial term, x squared minus 3, and then e to the x. They're multiplied. I'm going to do product rule. F g prime plus g f prime. So f is x squared minus 3. That's my first. G prime, the derivative of e to the x. E to the x. Plus g, which is e to the x. And then f prime, the derivative of x squared minus 3 is 2x. Okay, I'm doing critical points. So I will set this equal to 0. Now, before you go to distribute, you could, but I think an easier way to do it is there's two big terms here that are multiplied. GCF. They actually each have an e to the x in them. So I'm going to factor out an e to the x from each one. The first term I'll be left with an x squared minus 3 plus a 2x right here. Okay. And actually, I can now, this will be a trinomial I can factor. Let me turn it around or put the 2x first. Like that. If I put the 2x before the -3. It's actually a trinomial I can factor. So multiply get 3, so 3 and 1. And plus 3 minus 1. So I get x equals 1, I get x equals -3, and then e to the x equal to 0. To solve that one, I would do ln of both sides to cancel out the e, bring the x down. But ln of 0 is undefined. So you would actually get no solutions from this one. So if you try to do that in your calculator, it would not work. Two critical points. So these are, yeah, these are good. These are two of our answers. I'll just put CP. CP, critical points. Okay, and now to do the local extreme values. The local extreme, I'm just going to do the first derivative test. First derivative test is essentially when I do the number line. So -3 and 1. I'm going to choose some test values. Let's choose 0 in the middle, 2 on the right, and -4 on the left. Now, again, these test values always in the first derivative, never in the original. You can choose any of these. Like, look, all of these. This one, this one, this one. This are all the derivative. They're all equivalent forms. Doesn't matter which one. Let me see which one I think would be easiest. How about, again, it doesn't matter at all. How about this one? Let me start with 0. 0 is usually the easiest one to do. So e to the 0 is 1. E to the 0 power, 1. 0 squared is 0. Plus 2 times 0 is 0. Minus 3. So basically I get 1 times -3, which is -3. Okay, let's try another one. 2. 2. So it's the e to the 2, e squared. 2 squared is 4. Plus 2 times 2 is 4. Minus 3. That'll be 8 minus 3, which is 5. And so I'll get 5e squared. Which is positive, yeah. I don't need to know what it is. Doesn't matter. Just as long as it's a positive number, that's all I need to know. Or negative. Let's go ahead and take my word for it. The -4, when you plug it in, will be positive. Okay, and so now we can basically write down, we know the local extrema. The local extrema, something I forgot here. I'm going to tell us now. I'm crossing off my test points. Otherwise, students will say it's between -4 and 0. Well, no, it's just test points. So the actual critical, it's between your critical points at -3 and 1. So the local extrema occur at -3 and 1. The original function, f, was increasing up to -3, then decreasing, then increasing. So at -3, there's a local max. Okay, and then there's a local min at x equals 1 because it changed from negative to positive. I'm going to leave it at that on this one. Probably don't know about the global on this one. We have to look a little more into it. I want to just stop with this now that we have the local. It's a local test. Relative action then. Well, is there anything in it? So that's the end of this concept. So increasing and decreasing, monotonicity, and then the first derivative test will get us local max and net. Any questions on that?